Hello everyone. In this video we will continue examining topic 7.1 discrete energy and radioactivity, and in particular we will continue discussing the Segre plot and how it can be used to predict what kind of decay a nuclide might undergo. So in the last video we discussed the Segre plot, which consists of a plot of the stability of nuclides based on their atomic number and their neutron or nucleon number. And we discussed how the stable nuclides lie on a line that sort of bends upwards above the n equals z line, where n equals z means that the number of neutrons is equal to the number of protons. And as it turns out, it is possible to predict from general regions of the Segre plot what kind of decay you might expect an unstable nuclei to undergo. Now, there are other mechanisms for decay, and there are exceptions. So I don't want to say like this is a general rule, but we can predict roughly how a beta plus, a beta minus, and an alpha decay might affect a nuclide's position on this plot. Notice that we're not including gamma decay because a gamma decay will not change the position of a nuclide on this plot. It will simply take it from an excited nuclear energy state to a less excited nuclear energy state. So how do we predict this? Well, think about it like this. A beta minus decay, for example, is going to increase the number of protons and decrease the number of neutrons. That means a beta minus decay will take a particle down and to the right on this chart. And so it's very straightforward to see which particles might, or which nuclides might undergo beta minus decay. If you remember that the decay is going to take it from a higher energy state to a lower energy state. That is, it's going to bring the unstable nuclide closer to stability. And what that means is that all of these nuclides on here, okay, in order to get to that line of stability, they need to go down and to the right. They need to increase the number of protons and decrease the number of neutrons, which means that as a general rule, if you are above the line of stability and to the left, you will undergo beta minus decay. If you are a particular nuclide. The opposite is true for being below that line and to the right, you are more likely to undergo beta positive decay or beta plus decay. There's also another mechanism known as electron capture that these kind of nuclides undergo, which we'll discuss a little later on. So beta positive or beta plus decay is not the only thing that in particular these red nuclides might do to get to the line of stability, but it is a common mechanism. And then finally, alpha decay, right? Sorry, I should come back to beta positive decay. So beta positive decay, remember, takes a proton and fundamentally transmutes it into a neutron plus a positron, and as a result, takes you up and to the left. So it's the opposite process of that beta minus decay. Alpha decay, on the other hand, reduces the number of neutrons by 2 and the number of protons by 2. And so what an alpha decay will do is take you down and to the left, which means very heavy isotopes will often undergo alpha decay. It'll bring you this way along the chart. And so you see this kind of sort of decay among particles that are or among nuclides that are fundamentally too big, as they'll emit alpha particles. So from a Segre plot, we can predict roughly what kind of decay a particular unstable nuclide might undergo. Now, it is important to recognize, as discussed before, that what happens with unstable nuclides is that if they are created via some mechanism, so if you create an unstable nuclide up here, you'll notice that an alpha decay, a single alpha decay, will not get it all the way to the line of stability. And so what happens is you get what's called a decay series. So instead of decaying all at once in one fell swoop, as in the case of sort of these green fission dots right here. Usually what happens is that you actually get a series of decays, and your parent nuclide becomes a daughter nuclide sort of further down the chart in a series of beta minus, beta positive, or alpha decays there. So what you'll see is that there is a sequence of radioactive decays composed of these fundamental types, alpha, beta, and gamma, from an unstable isotope to a stable isotope. And sometimes you can see that there's more than one way of going about it. So if this is the decay series of thorium, then it will need to end on a stable isotope, and it will undergo several decays in order. Some alpha decays, some beta minus decays, some more alpha decays, and then it might even undergo more than one pathway. So it can beta minus decay, then alpha decay, then beta minus decay again here, or beta minus decay twice, and then alpha decay once. So you'll see more than one path in a decay series. It is important to recognize that this chart right here is an example of a small section of a Segre plot where the nucleon number or mass number is being plotted rather than the neutron number. That is why these beta minus decays are actually horizontal on this particular chart, because the nucleon number is staying the same in a beta minus decay rather than decreasing. It's important to note that this kind of chart has exactly the same information as this Segre plot, and that's why sometimes you'll even see the Segre plot written in terms of the neutron number, in terms of the nucleon number rather than the neutron number, as shown there.